discuss Bernoulli's principle. Consider a fluid moving in pipe of varying cross-minus sectional area. Let the pipe be at varying heights. We now suppose that an incompressible fluid is flowing through the pipe in a steady flow. Consider the flow at two regions, one that is BC and two that is DE. Let fluid initially lying between B and D. In an infinitesimal time interval delta t, fluid which is initially the speed at B has moved a distance v1 delta t to C. v1 delta t is small enough to assume constant cross-minus section along BC. In the same interval delta t, the fluid initially at D moves to E, a distance equal to v2 delta t. Pressures P1 and P2 act on the plane faces of areas A1 and A2 binding the two regions. The work done on the fluid at left end BC is W1 equals to P1 A1 V1 delta T equals to P1 delta V. Since the same volume delta V passes through both the regions from the equation of continuity, the work done by the fluid at the other end dE is W2 equals to P2 A2 V2 delta T equals to P2 delta V. So, the total work done on the fluid is W1 minus W2 equals to P1 minus P2 delta V. Some part of this work goes into changing the kinetic energy of the fluid, whereas some part goes into changing the gravitational potential energy. If the density of the fluid is rho and delta m equals to rho A1 V1 delta T equals to rho delta V is the mass passing through the pipe in time delta T. Then, change in gravitational potential energy is delta U equals to rho G delta V H2 minus H1. The change in its kinetic energy is delta K equals to 1 by 2 rho delta V V2 square minus V1 square. Using the work energy theorem, we get P1 minus P2 delta V equals to 1 by 2 rho delta V V2 square minus V1 square plus rho G delta V H2 minus H1. We now divide each term by delta V to obtain P1 minus P2 equals to 1 by 2 rho V2 square minus V1 square plus rho G H2 minus H1. On rearranging this equation, P1 plus half rho V1 square plus rho G H1 equals to P2 plus half rho V2 square plus rho G H2. This is Bernoulli's equation. We may write the expression in general as P plus half rho V square plus rho GH equals to constant. In words, the Bernoulli's relation may be stated as follows. As we move along a streamline, the sum of the pressure P, the kinetic energy per unit volume V square by 2 and the potential energy per unit volume rho GH remains constant. Few assumptions. First, there is an assumption that no energy is lost due to friction. But in fact, when fluids flow, some energy does get lost due to internal friction. This arises due to the fact that in a fluid flow, the different layers of the fluid flow with different velocities. These layers exert frictional forces on each other, resulting in a loss of energy. This property of the fluid is called viscosity. Second is that the fluid must be incompressible, as the elastic energy of the fluid is also not taken into consideration. Third, Bernoulli's equation also does not hold for non-minus steady or turbulent flows, because in that situation, velocity and pressure are constantly fluctuating in time.